Thank you all for coming. This is Max Argus's presentation. He is a postdoc at the University of Freiburg.
Should I start now? Okay. Yep, good. I'm happy to be presenting here. So let me just get right into my presentation. So I wanted to start off with this quote, which you might have seen going around on Twitter some time ago. We have very strong AI models that are very good at doing a large number of things, but somehow, interestingly, they're quite good at like writing poetry and generating nice images, but not yet as good as we would like them to be in like doing our laundry and cleaning up. So this is kind of a interesting framing that I wanted to start off with. Because I'm going to be talking about robot manipulation, which is like one of these things which are obviously not quite sufficient yet for achieving those goals. So I'm going to be talking about training VLA models for robotic manipulation, and I want to be looking at using simulations and how to get generalization to the real world to happen as effectively as possible. So I've structured my talk into 3 different sections. I want to start off with a bit of background information on the work that I've been doing previously, as well as my PhD thesis. Then go into this current work where I'm working with VLAs, and then from that transition into kind of a longer term outlook and discussion of the things that we maybe want to do in the future. So starting off with my background, I'm actually studied physics at the University of Heidelberg. And after that, I did my PhD in computer vision at the University of Freiburg with the research laboratory of Thomas Brox, which you might know because of optical FlowNet or something like that, or UNet. Those are the most famous works. And I've also interned at UC Berkeley and a number of companies, including the German Aerospace Research Center. And in my PhD thesis, I was working on robotic manipulation, and what I did during that thesis was like having this collection of very different approaches to the robotic manipulation problem, ranging from like classical grasp planning to visual servoing and reinforcement learning. And it's kind of this very interesting scope because it shows like the wide variety of approaches that we can use to try to address the manipulation problem. And I think these other methods, while they're not super current at the moment, also are very relevant to know and understand well, because they can give us like good inspiration for making big machine learning based algorithms work well. And just for the sake of time, I want to not look at the classical work that much, but more focus on the visual servoing and the reinforcement learning work that I did. So the classical work was using this humanoid mobile robot with this 4-finger hand, which had quite a high number of degrees of freedom. And I just wanted to put this teaser picture out so that we can potentially talk about it later if we're interested in this as well. But turning the clock forward a bit, something I did at a later stage with visual servoing. And I don't know how many of you have heard about visual servoing, so I just wanted to give a like super brief introduction into this approach and explain how it can be used for manipulation, and yeah, then just move forward from there. So in visual servoing, we have the setup where we have a robot arm and we have a camera attached to the end of that robot arm, which produces an image that we see at the moment. And then for servoing, we have a goal state, often given by an image as well. And the aim is to move the robot in such a way as to align the currently seen image with the desired goal state image. And a lot of this work involves kind of finding control mechanisms for the robot and like extending the inverse kinematics with like the Jacobians of the cameras and the markers on the objects. But for the sake of that presentation, we just kind of want to ignore all of that and look at it more from a computer vision perspective. And from a computer vision perspective, what we have a lot in this classical visual servoing world is like very manually defined structures for which we learn like pose estimators, which give us the input into our visual servoing algorithm in order to actually be able to interpret these high-dimensional images before we had computer vision methods. But nowadays we have very good computer vision algorithms. And the question is, how can these be used to kind of enable visual servoing without having to design any of these manually defined features or without having to look at just objects which we know the geometry of? And we have the setting where we have our live image shown here coming from the robot, as well as our demonstration goal image, which we want to have. And one of the algorithms that we have from computer vision is this optical flow algorithm, which gives us dense correspondences. Which gives us dense correspondences between two images. And normally these optical flow algorithms are used between successive frames of a video to find the motion, but we can kind of also use them out of scope to find correspondences between demonstrations and these live images, which we record at a later point in time, and get the dense correspondences between these two. And these dense correspondences bring us quite far along the way of solving this alignment problem, because if we are then interested in just a specific region of this image that we observe here, for example, like the screw structure, which is shown, I don't know if it's really clear, we can kind of focus in on only this foreground part of the scene and then align ourselves really just based on the subset of just this foreground part of the scene. And the way that we do this is we use RGBD observations, and we use our dense correspondences, and we segment with our foreground segmentation, and then we get 2 point clouds, and then we can compute the rigid transformation which aligns these 2 point clouds, and that's also the transformation which we can use to control our robot to put us into the right relative position. So then we could ask ourselves, what does this have to do with manipulation? So it's not like directly applicable, but if we consider having a demonstration video of several frames, what we can do is we can align with one frame of this demonstration video. And then when we have good enough alignment, we can then iterate to the next frame of this demonstration video. And if we successively do that, we basically track the relative motion of the end effector with respect to an object, or with respect to a container at a later point in a trajectory, and we can basically incrementally follow this trajectory using this visual demonstration information that we have. So feel free to ask any questions in case something is not clear during this as well. I know I'm going quite quickly. So just to give an overview of the whole system again, we have a live observation shown on the top. We have a demonstration observation. We first compute the flow. We're only interested in moving with respect to a particular object, not with respect to the table, for example. So we mask our motion, and then we combine these mask correspondences with depth information to get 2 point clouds, compute the rigid transformation, and send that to the robot. And the nice thing about these algorithms is that because optical flow is a pixel level algorithm, we can move with more or less pixel level precision, which is a lot better than what many of these like reinforcement learning algorithms will give you out of the box. But you have to stay quite close to your demonstration video in order for this to work, because optical flow is like quite restrained in the degree that it finds these correspondences.
I have a question.
Yeah.
What does, because like I guess you're using optical flow, does like light perturbations affects the learning significantly, like or any changes to lighting?
So actually, optical flow is trained with a lot of like image augmentations, for example, like image intensity and color. So optical flow is out of the box quite resistant to these. And you can also, especially in scenes that are relatively sparse, you can also get like cross-object generalization from like apples to oranges or something like that. The optical flow will just find the closest correspondence. But at some point it breaks down. And just like another thing about these servoing algorithms, they kind of exist as this local tool, but it's also possible to kind of like extend their region of application by taking long demonstrations and cutting them into small sequences. And we have initial frames and end frames. And by comparing the similarity of those initial and end frames, we can actually construct a graph and combine elements from different demonstrations or use this graph to basically get us from a arbitrary initial state to an end state, given that we have like any demonstrations which take us from A to B. The other thing that we can do, also very similar to this visual servoing work, is to learn from human demonstrations. And here we basically extend this idea and we go away from the setting where we have an end-of-arm camera, and we take external videos of humans manipulating objects. And we also use a semantic network which gives us object segmentations, hand segmentations, and container segmentations, which was trained on like the HANS 24 dataset. And this approach works in a very similar way. We start off here with a demonstration recording. We apply the semantic segmentation network to give us these segmentations. We refine them slightly with segment anything, and then we track the motion of the object over the course of this video. So then we have a trajectory which is relative to this object. And we can do this offline. And then during inference, we see a new input scene. And we look at our semantic segmentations for our objects as well as our containers. And we find these objects again in our new input scene. And then we take our trajectory, which is moving the object into the container. And we paste this trajectory into this new scene, once relative to the container and once relative to the object. And then we have these two trajectories, and then we warp them together to get a final trajectory, which we can move our object by. And here again, we get this direct one-shot imitation from a human demonstration, which we can then get this good trajectory, which we can execute on a mobile robot, for example, making use of grasp planning and inverse kinematics to do the actual grasp and to navigate us along these trajectories. So what does this look like in practice? We have the scene here, for example. We have the mobile robot here, which is located on this movable tower. It's grasping the Coke can and putting it on the tray. So this also works relatively quickly. We haven't accelerated this video at all. And in this video here, we really drastically changed the position of this container tray that we use. And we can already see like some failure modes because we don't do any collision checking or anything like that. And if you want to call that a success or a failure, it's kind of open to you and dependent on how you want to define those. But that like shows how this simple idea of visual servoing is actually like quite widely applicable to manipulation problems as well. So the next thing I want to talk about is reinforcement learning, because it's also something that you're doing at your lab. And this was quite early work that I did in like 2017, 2018. And in this work, we were just like trying to apply reinforcement learning algorithms directly to simple manipulation problems like stacking cubes or like putting things into containers. And the question here was like how to get this to work at all, because there wasn't like so much literature on getting this to work well. And the strategy that we chose to follow is to try to construct this curriculum to try to keep the success rate of the current task that the reinforcement agent is trying to solve at around 50%, because we thought that this would be the region where the robot is learning most effectively. And how do we influence our the difficulty of our task? We chose to do it by using a very small number of human demonstrations and initializing the initial state of our reinforcement learning agent in the beginning at a state which is really close to the end of that human demonstration. And in that case, for example, in block stacking, he only has to open up the gripper in order for the stacking to be complete and in order for there to be a reward signal. And when that starts working very well, we can make the problem harder by sampling initial states which are further away from the end of the trajectory. For example, here, where he just has to, where he already has the object grasped and only needs to move a small distance. And we can extend this till we sample really at the beginning of demonstrations. And we can also control the difficulty by changing the degree to which we do domain randomization. And for this work, we found that really being close to this 50-50 success-fail range is the optimal zone for these reinforcement learning algorithms to work as efficiently as possible. Another thing we did in reinforcement learning was looking at sample-efficient off-policy reinforcement learning. And in this work, we were looking at the classical gym tasks of continuous control of like the 2D walker or the humanoid or the hopper or the ant environment. And in this work, we looked at how to apply normalization techniques. So specifically, we looked at applying batch normalization to the TD3 algorithm. And here we found that if we do batch normalization in a specific way by concatenating both current observations and our samples from our replay buffer, it was possible to completely get rid of the target networks that we use in off-policy reinforcement learning usually, and thereby accelerate the speed of the training quite drastically. So that kind of ends up, yeah.
Can you give us more intuition why this spatial normalization stable the training?
Maybe can I answer that at the end of the presentation, maybe?
Yeah, sure.
Okay. So that kind of wraps up what I wanted to explain about manipulation. And I wanted to focus on manipulation because you're starting to work with that as well more. But really, I've done like quite a wide set of work, including things like hand pose estimation, explainable AI algorithms using things like concept networks, out of distribution detection and medical computer vision, and things like looking at clip training. So I just wanted to put those out there in case there's anything you want to talk about. But what I want to go to next is the current work. And I basically had completed a lot of this manipulation work, and I was supervising other PhD students who were doing these quite broad range of topics. But I wanted to work with vision language action models because I saw that they were very promising and also increasingly being applied to manipulation. But before starting, I kind of wanted to take a step back and look at kind of the guiding principles, and there are like two very important things came to mind. One is the bitter lesson from Richard Sutton, which you've all probably seen already. But I just wanted to use this opportunity to kind of point out this interesting fact that in this original essay, Sutton is focusing specifically on leveraging computation instead of data, which is quite interesting. And I think it's really this consequence of this early reinforcement learning work that people like Sutton were doing, existing in the context of games like chess and backgammon, which had like this very restricted set of states. And thereby, like, computation is the way by which you visit all the possible states that you could potentially reach. But that's just like a detailed footnote, but we generally have the situation like data is incredibly important. And I mean, that continues to hold today. So we have this other essay, which maybe also you already saw, which is basically saying that the relevant part of all of these different AI models that we have, like Llama and ChatGPT, the relevant part is really the data set which we use for the training. And we can observe if we train generative models, for example, these text models, or for example, image generators, that these models kind of tend to converge on the same results independent of the architecture that we use. So the data is very important. How does that play into training VLA models for manipulation? I'll get to that in a second. So I started off with this project in manipulation, and kind of what I didn't see yet at the time was just kind of like an off-the-shelf algorithm for doing manipulation, which you can download and run on your own robot, like independently of what kind of end effector it has or what kind of arm is attached to your robot. And I also wanted something which has this experimental setup where I can run experiments quite quickly, and I can also benchmark the performance of my algorithm relatively easily. And within these like high-level aims, I also had specific questions. I definitely wanted to fine-tune an existing VLM, because anything else is a bit insane. I also, coming from visual servoing, I was quite interested in these camera space actions, because I think it's something that really makes you generalize very well to be independent of the position of the camera on the robot. The downside is you need to have extrinsic calibrations. And the other things I was interested in is like having depth as the input modality and looking at very diverse object sets. So given the starting points, I kind of started off using the Gemma model, the polygemma model, because it has this interesting feature of also being trained to do segmentation and having these specific tokens which correspond to image positions and segmentation outlines, which are like already quite a good starting point for if you want to do camera-centric action prediction. But kind of the important thing in this project was also that I'm working on this project by myself, and these vision language action models are like really big things. So I also had to take a lot of care in kind of carefully deciding how to manage the scope of this project in order to be able to examine the things that I'm interested in. And so here I'm also working in an academic context. So I just wanted to point out that I'm not like aspiring to train a full foundation model at this point. I want to like analyze these specific things. And there's a number of differences between these canonical foundation models and my work. Mainly, I'm using simulated data. For now, I'm using just a single task, and I'm not doing continuous control. I'm just predicting like small trajectory snippets with 2 key points. And I'm just doing like full supervised fine-tuning of these models. So what does the whole training setup look like? It's basically like the canonical VLA setting. You have an input image. In this case, I'm using just a single external view. We have a text instruction of the action that's supposed to be performed. We have an encoding of the current robot state. And we give that all into our model, and then what we predict using our model is a set of waypoints. And in this case, I've basically recycled the polygemma detection and segmentation waypoints in order to use them for predicting TCP positions. And the way I've done it is I've predicted just two waypoints. So I predict the 60 poses. So it's like 2 times 6 tokens. So I'm just predicting 12 tokens, which is like a very small number. And in theory, you can definitely extend this to predict more, to predict longer trajectories. And what I'm doing is I'm also not fine-tuning the full model. I'm just fine-tuning the attention layers, which seems to work relatively well. And I'm using a training data set of about 140,000 images, which I trained for 1.2 epochs. And kind of the first insight I had doing this was that actually like the tokens matter. And when I was using the same tokens for training the position as the orientation, the system kind of ended up just learning either the position perfectly or the orientation perfectly. And I think this is really like a symptom of the variance of those two different predictions being completely different. So like after I changed that, it was working better, but I just wanted to use that as a small example that like fine-tuning these models is not just super easy. It's also like a bit difficult and finicky. But just to say a little bit more about the data set. So I started off using the many skill simulator. I started off using a set of shapes, which is inspired by Clever. So 2 different shapes, 8 different colors, and 2 different sizes. And I only had one action, which is like move X onto Y. But like through randomizing the shapes, I have quite a high diversity there. And I also randomized very strongly the position of the external camera. And in these images, we can see some examples. And here in dark green, I've just like tried to plot the 2 key points, which are relevant to this trajectory that the robot has to follow. I kind of set this up and fine-tuned the model on this, and it took a bit of work to do. But in the end, the model is able to predict these key points quite well. And kind of solve the task that I wanted it to complete, and I can evaluate it in simulation as well, which is quite good because it's much nicer than like evaluating things on real robots, where it's very difficult to get like statistically representative numbers. So that's kind of the first thing that worked. And from that basis, I just kind of wanted to see, oh, if I apply this model to real data, like how well will it work? And I didn't expect it to perform very well at all, because like is shown in the previous slides, this domain is like super restricted, and we only have these really basic geometric shapes. But if we kind of get a subset of the Droid data set in this case, which isn't like too different from that data, we can see that like this 0-shot transfer of this VLA model is possible, and it actually like manages to bridge substantial domain gaps as well. For example, if we look at the text, I've just like highlighted in red all of the words that don't appear at all in my training data set. And it's like most of the words of these text descriptions, but still the model kind of learns that it needs to complete this task, and it works despite this domain shift, which is quite impressive. But that was just basically applying it directly as is to this real data without thinking about it or trying to optimize for that at all. But here we basically have this like classical setting from computer vision where we have this generalization problem, and we can kind of analyze both of our data sets in quite a structured way and kind of try to get a better feeling for how they differ and try to kind of align our simulation a bit with the real world in order to improve this performance. And we can...
I have a question.
Yeah.
I don't interrupt. But just now in the example, you showed a zero shot. It wasn't clear to me, but you train everything in sim and you deploy it zero shot in real on that camera view.
So what I've done here is I've evaluated the model at predicting the trajectory from the human demonstrations. So I'm not actually executing it with the robot.
Oh, so you're predicting the line drawing.
Yeah.
Like the points,
Yes.
rather than running the execution of the post. Okay.
Yes.
Okay.
So I think, so we'll see it in the results a bit. I think the results are not quite good yet. Like it needs to be improved a bit based on this like offline evaluation. But I think these are quite promising results to indicate that like it's not like degenerating completely. And if we kind of curate our data a little bit and optimize our model, then it should at some point work also zero shot on real robots. But for now, this is just evaluated on the data. Yeah.
So maybe you have already mentioned that, but yeah, I was wondering, do you do the end-to-end fine tuning for the entire polygamma too, or you freeze the, like for example the visual encoder, or do you do any curriculum training throughout the training stage?
So what I do is I fine tune only the attention layers.
Gotcha. The attention layer in the polygamma too.
Yes, exactly.
Gotcha.
Everything else I leave frozen, and up to now it seems to work reasonably well. I think more I have to kind of work on the data than...
So what would be the reason you only fine tune the attention layer? Like what's the intuition? Like have you tried fine tune with other component and then find it's like doesn't work and then
So one reason is that it's easier for me because it fits on my GPUs more easily if I do this.
Yeah, this is a fair.
I haven't done a full sweep. So basically what was happening is I put in my simulated data and the loss goes down really strongly and the predictions on the simulated data are super good. So I have the feeling like the learning is not the bottleneck at this point. I think the bottleneck is more the fact that the data is more different. So I'm trying to focus on that a bit more.
Yeah.
Like I think once I get to the point where the predictions on the training data set aren't as good, then I think I'll also start to look more at optimizing the training.
Yeah.
Is there any like okay, never mind. That's another question.
Yeah, just a follow-up question. So do you mean the efficient training such as LoRa or the other some quantization training for fine-tuning the attention layer, or just a full fine-tuning?
I'm doing a full fine-tuning. I tried LoRa and I wasn't getting good results, but I also tried LoRa before I switched my token representations to have separate tokens for position and action. So kind of in a way, these results, I would have really liked to have had like an extra week or two, because I think I could have like presented much more structured results, but this is what I have now. So I'm just gonna, but like having a more structured evaluation, I even haven't done like full like learning rate sweeps. I'm really at the beginning of this, and that would be like the starting point. But just to come back to the presentation, so like we can kind of just quantify how well our training and our test domain overlap to get a sense of like what this domain gap is that the model has to bridge. And here we see if concerning the X and Y positions on the image, they're very similar. The depth distributions kind of overlap. For the angles, I think there's still like a 180-degree difference in the droid angles versus the simulation angles, which still needs to be fixed. And also, if we look at the frequency of the text words, the distributions are completely different. But the model manages nonetheless. We also have a setup now with this real data where we can do quantitative evaluation of how close we are to predicting the correct trajectories on the real-world data. And here we see that our X and Y positions that we predict are actually relatively accurate in pixel coordinates, but the depths that we predict are really not accurate at all. And the reason for this is kind of obvious. So we're taking this model which just gets the RGB input image, and it is able to predict the depth because in my training set I have objects of 2 definite sizes, and it can learn to distinguish what the sizes of these objects are, and from that infer the depth that it needs to predict for these actions. But if I change the object distribution, that's not going to work at all. So it fails in this case. And basically, one of the things I need to do next is now go to a much more diverse set of objects, where I can then hopefully also start to see this pattern of the depth predictions failing in the validation sets for these objects. And that would then be like the cue to start also including depth information into the model in order for it to be able to predict more precise depths.
I have a question, a quick question, I think.
Yeah.
Going back to the previous slide where you actually talk about the depth error. So essentially, like when people usually train VLA models, they try to train with a bunch of data of like delta posts with image. And obviously, like that requires a lot of resource, but the idea is to sort of learn some kind of representation to understand depth from like understanding a depth scale, camera extrinsic, intrinsic through this learning process. So in that case, then maybe occlusion might not be that much of a problem. But I guess what you're trying to do is you're trying to do like predicting the points and then doing some kind of visual servoing with the depth. So then there might be problems with like occlusions or like partially occluded objects, and then the depth will not really work. So how do you handle something like this?
So here I'm not doing any visual servoing at all. I'm just getting my VLA to output these 2 waypoints, and I'm sending these 2 waypoints to the robot. So the end effector moves to this position. It moves to the first waypoint, it closes the gripper, it moves up a bit, and then moves to the second waypoint and opens the gripper there.
So are you predicting the depth also? Because you need to,
yes,
just on the image plane, you need to know where you go.
So to do that, I need to predict the depth. So I'm asking the model to give me a metric depth output in centimeters. Like how far away from the camera should the end effector go?
Then what about rotation? What about rotation?
I'm predicting the rotation also relative to the camera.
Oh, okay. Thanks.
And I'm using the extrinsic calibration to convert that into robot coordinates, and then I'm giving it to the robot. Yeah.
Thanks.
Yeah, so where was I? So depth works at the moment because the model is overfitting on my selected shapes, but we want to test this algorithm in a much more general case. So we want to have also like a diversity of objects, and we also want to randomize the sizes of these objects so that we don't just like overfit completely on a small subset of objects. And for this, Rose helped me a bit to look at the Observerse assets that you had. And I set up the many-skill simulator to load the Proxor environments and to load the Observerse assets into these Proxor scenes. And I basically combined this with my existing setup, which was randomizing the positions of the cameras always and like looking at these scenes. And I'm not quite there yet to have this data generation set up to the point where I can generate a training data set, but I'm like super close to this. And it is kind of working, and this is running in the physics simulation as well. So I'm like quite happy with these results. And the rendering that you see here now are just the YCB objects, so I'm happy to talk about that later as well. But the observers objects also work, and they have the correct size. It's a simulation. I was talking about depth. Also, what we can obviously do is input the depth images into our VLA model. So I've just rendered a few examples. This is something that I'm basically doing at the moment. Also, like very basic things like RGB augmentations. I've shown some examples here. I haven't trained my VLA model with those yet. But those are all on the list. And we can also look at something like pose estimation, which uses randomized background images for inspiration and like test if this helps us to get better performance on our real data. So these are all kind of very close lying next steps that I'd like to have a look at. But basically, it's the situation where we look ahead and there's like a very large number of unsolved problems still ahead. And just like in preparing for this presentation, some of the things that I was thinking about was like how similar we want to make our VLM training to our VLA training. And if we can like find a set of tasks which we can convince the VLM people to include in their training. For example, so I don't know what they should be exactly, but maybe like going from detection regions as input to finding out the classes of the object that is in that detected region, or to add 3D data to the input of the VLM model in order to like make it quite aligned with our VLA model in the end. So that's a potential thing that could be done. Going back to the visual servoing that I talked about, I think conditioning also by demonstration videos is something that we definitely want to have long-term in VLA models, because if we go to an industrial setting, for example, we'll just have like components for which we don't have any very clear text description. Or let's say if we have like a faucet which we have to move in a particular way, we just want to have the ability to include a demonstration of that in our VLA model in order to have this task solved, and not like have this requirement of basically having everything in weight. I think there's one thing I've thought about, which is probably quite interesting, is when we do our conditioning with our text, the question is like, how fine-grained do we want our text annotations to be? And if we can kind of have quite atomic actions and have kind of a high-level planning system which turns our like move X onto Y into more fine-grained things, like first pick up X and then move to Y and then open gripper or something like that. And I'm kind of curious as to like what a good solution is there. In terms of like network architecture, one thing I potentially would find interesting is if we can like include in the input of our model like the result of some like higher level planning algorithm, so that we don't have the structure of having like the long-term planning like put on top of the manipulation, and all of the actions have to go completely through the long-term planning model, but the long-term planning model kind of defines a short horizon goal which goes into the model that then outputs the actions. One thing I'm asking myself is like how deterministic the training data needs to be, because in simulation it's like very easy to control the degree of deterministicness, and like at which point does it help to start using diffusion, and like how do we want that to work? There's this permanent question of what the observation spaces should be. Do we want to have wrist cameras? Do we want to have depth as well? If we have external cameras and width cameras and depth for all of them, we end up with like 4 input images, which is like quite token expensive. So that's like not entirely clear. Do we want to have forces as well? do we want to have some kind of architecture where we have the option of like zooming in on the region of an image and looking closer? Because if we go back to the real data, often the objects that we manipulate are quite far away, and these images are big, but if we kind of resize them to 224 by 224, the amount of pixels that the vision model gets for the objects are quite small in the end. So like at some point, I think that's going to be a limit in actually like computing good grasp positions. So I think there's basically like a ton of open questions, and I'm quite interested in figuring out strategies to solve all of these problems. So yeah, that wraps up my presentation. So thank you very much. Like I said, there's a lot of things. I'm happy to talk about whatever you want to.
Actually, I had a quick question. Thank you for the talk, by the way. It was very interesting. But if you go back to the orientation representation from the input and output of the VLA, how do you represent it? You mentioned 3 tokens. Is that just yaw, pitch, roll?
So I don't use Euler angles. I use rotation vectors, which is like the axis angle representation, but
Okay.
it's been like scaled to the degree of the rotation.
And these are this is a rotation vector in the camera frame.
Yes.
Okay.
I mean, there's basically an encoding function, and you can switch out the encoding function, and then you can get the orientations in robot frame or anything. Like, it's quite flexible, but what I'm using at the moment is in camera frame.
Okay, thank you. That makes sense.
Yeah.
Oh, I also had a question earlier about Kuha. Actually, the same as Kuha's earlier question of the how does your modification to, I think it was SAC, remove the dependence on a target network?
So the target networks in SAC aren't actually like a principled decision to include them. The situation that we have is that the training dynamics are unstable, and we need to include the training dynamics in order to prevent the p-value predictions from exploding. So the way it helps is that the batch normalization is stabilizing this training because we have less of this distribution shift. So what we're doing in Q-learning is we're combining Q predictions, which are based on states and actions from our replay buffer and states and actions from our current policies. And those actions can be very different, and that causes a big distribution shift. And if we go to the case where we have one Q network and we put both of those in, we don't have this like going back and forth between these two different distributions. We continuously work in one distribution. And just like batch norm is like a regularization, and that also stabilizes learning just by itself. So in a way, like the positive effects that we are getting from batch norm, like give us the freedom to get rid of the target network.
I see. Thank you.
Yeah.
Awesome. Thank you so much, Max.